In this video, we explore problem 1.1 from the textbook Quantum Mechanics by Dr. David J. Griffiths. Quantum mechanics textbooks often start with a review of probability theory due to the probabilistic nature of the subject. To set up our problem, let's begin by considering the following scenario. Suppose there is a room with a total of 14 people of ages ranging from 14 to 25. Using terminology from probability, we can say that these 14 people represent our sample size. In our scenario, let's now suppose that we ask each person in the room for their age, and then proceed to plot it using a histogram. This results in the figure where we have the ages on the x-axis and the number of people of that age on the y-axis. By inspecting the chart, we can learn a few things. First, the age distribution is skewed to the right. This suggests that there are more older people in the room. And second, we can determine that the most common age in the room is 25, as its corresponding ordinate is 5. This relates to a fundamental concept in probability theory, namely probability. And in quantum mechanics, probabilities are everywhere. So, in the first problem, we're going to compute the expectation value of the random variable j. In our case, j takes the potential ages a person in the room can have. And these ages, as we saw, range from 14 to 25. So for part A, we can see that j, the expectation value of the random variable j squared, is simply the sum of j going from 0 to infinity of j squared times the probability of the random variable j. And similarly, the expectation value of random variable j is simply the sum of j going from 0 to infinity of j multiplied by the probability of j. Notice that the probability remains independent on any transformation of the random variable j. More generally, we can say that the expectation value of some function of j is simply the sum of j going from 0 to infinity of the function f of j times the probability of j. This is simply a useful generalization that will not be applied in this problem. Now, for this, we're going to leave it in symbolic form, but if you wanted to, you can go through each possible value of j, and we know that the set of possible values of j is 14, 15, 16, and 22, 24, and 25. Okay, now for part B, we are asked to determine the uncertainty of random variable j, and then use equation 1.11 to compute the standard deviation. Now, equation 1.11 is simply the variance, and it is defined as the expectation value of the square of the uncertainty of j. Okay, and so using the formulas from part A, we can learn, specifically the generalization, we can learn that the expectation value of the square of the uncertainty of j is simply the sum of j going from 0 to infinity of the square of the uncertainty of j times the probability of j. Okay, and so to compute this, we first have to compute the uncertainty of j, and as we also saw in the textbook, this is simply the difference between the random variable j and the expectation value of j. Now, to compute the expectation value of j, we use this formula right here, and this comes out to be 21. And the value of 21 was obtained by simply summing over all the possible values of a j times the probability of each individual value of j. And similarly, we compute the expectation value of the square of j to be 460. This letter quantity is going to be relevant in the next part of the problem. All right. So now that we have this, we can compute the variance as follows. So we have the first value of j, which is uncertainty of 14 squared times the probability of j. Now, what is the probability of random person in the room being age 14? Well, it's simply 1 over 14, since there's only one person with age 14. And this is similar to subsequent ages, namely, how many people in the room are there of age 15? 1 again. So we continue like so for all successive possible values of j. We have 3 people in the room, age 16. All right. And to compute the uncertainties of the individual values of j, we simply use this formula right here. And after substituting it into the corresponding places in this equation, we find that the variance comes out to be 19. And from the variance, we can really easily obtain the standard deviation, which is simply the square root of the variance, namely the square root of 19, or about 4.36. All right, so this solves part B, where we were asked for the uncertainties as well as the standard deviation. And for part C, we are asked to verify that equation 1.12, namely the variance squared, is simply the difference between the expectation value of the square of j and the square of the expectation value of j. So let's check. We can see that the variance, we obtained it to be 19, and we obtain the expectation value of the square of the random variable j to be 460, and the square of j, 21 squared, is simply 441, which turns out to be 19, and thus we can say that equation 1.2 is true. Alternatively, we could derive the expression, or we can derive expression 1.12 by simply substituting the corresponding expressions for the expectation values and then simplifying, and that is left as an alternative exercise for you, the watcher. Okay, and with that, we conclude problem 1.1 from the textbook. Okay, so with this basic understanding of probability and expectation value, we are not equipped with essential concepts, and we are ready to dive into more intricate problems from the textbook in our upcoming videos. So if you are interested and you are new to my channel and enjoy this video, please consider subscribing to join me on the exciting journey through physics. I'm new to YouTube, but don't forget to hit the like button and drop a comment below. On this channel, I'll be creating series for different physics textbooks, starting with quantum mechanics, which is my personal favorite. So if you have a specific problem or topic you're curious about, feel free to suggest it in the comments or shoot me an email. I'm here to help and eager to explore the topics that interest you the most. So with that being said, thanks for tuning in, and I'm looking forward to seeing you in the next video.